Okay, we have started our consideration of this hyperboloid, hypersurface, which is actually hyperboloid, as we will see in a moment. Where A and B run from 0 to D, so it's a hyperboloid embedded into D plus 1 dimensional space, Minkowskian space with symmetric. So, and we made observation that it is a space of constant positive curvature for two reasons, that under the change of x0 out of this x0 to I x d plus 1, it is mapped to a sphere, d-dimensional sphere embedded into d plus 1 dimensional Euclidean space. That's the first way of observing. A second observation was made that this is a homogeneous space, which is SOD1, isometer of the space SOD1, which is Lorentzian group of d plus 1 dimensional Minkowskian spacetime, over SOD minus 1, 1, which is a stabilizer, a subgroup of this group, which doesn't move arbitrary point of this space. And this tells us that every point in this space is equivalent under the action of this group to every other, and every direction is equivalent to every other, up to the difference between space-like and time-like directions. So there are several other observations that can be made on the basis of this is the following thing. How do we define, using this Wick rotation is convenient to further moves, how do we define distance on the sphere? On the sphere, we define the distance as follows. So if we have a two-dimensional sphere, it's easy to see. So the distance between arbitrary 2 points on the sphere of radius r is nothing but the r times the angle, this angle between two. So we have our origin, two radius vectors directing to the 2 points 1 and 2, and the distance, geodesic distance, is just this segment, which is which segment I will explain in a moment. The distance is just this angle measured in radians times r. So the geodesic distance is just r theta, where r is the radius. But how do we define this distance? We take 2 points. So we have two vectors, x1. It is a vector defining this point. So because it's laying on the sphere, it obeys this. We have x2, second vector, x2, which is laying on the sphere. And to define this, we just take the scalar product of x1 to x2. So x1 on the sphere, we have this, x1 times x2. Just scalar product gives us r squared times cosine of this guy, which is nothing but the geodesic distance between these points divided by r. Cosine of this angle. This theta is just equal to this, because this is L12. Great. So in fact, Wick rotation helps us to see that the same procedure can be applied in this case, even without drawing the pictures. Well, this is, in d dimensions, this procedure on the spheres is similar. So using Wick rotation, we can define so-called hyperbolic distance. If we have two x a 1 obeying the relation this, both x1 and x2 are obeying this condition. So laying on this hyperboloid, this is a hyperboloid, we will see in a moment that this is a hyperboloid. And so if they obey this, we can define the hyperbolic distance between them, taking the scalar product of x1 to x2. We can define cosine of h times L12, where L12 is the geodesic distance between points on the hyperboloid, divided by h squared. So this formula can be obtained from this one under the Wick rotation and change of r to 1 over h. So the thing is obvious in this case. Now, to see the fact that this is a hyperboloid, let me just draw it for the case when d equals to 2. So when d equals to 2, we have the following situation basically. We have x0 squared with a minus sign plus x1 squared plus x2 squared. x2 squared equal to h to the second power, which then tells us that for every x0 we have a circle, x1 squared plus x2 squared is equal to h squared plus x0 squared. So on this space of when we have x0, x2, x1. So this guy is nothing but the one-sheeted hyperboloid as follows. So it has minimal radius of the circle at x0 equals to 0. So this is just 1 over h. But then as x0 is increasing, the radius is increasing to infinity and increasing to infinity towards backward in the x0 direction. So under Wick rotation, this hyperboloid is mapped to the sphere. And this we can relate geodesic distance to the hyperbolic distance using this formula on, well, this is a spherical distance probably. It's better to call this spherical distance. Hyperbolic distance is this quantity. It's called Z12, unlike this one, which is a geodesic distance. And one last thing that I have to say is the following. How do we obtain geodesics on the sphere? We take a plane which passes through the, suppose we want to find a geodesic between point 1 and 2. How do we do that? We take a plane which goes through these 3 points, this one and this two and this one. There is a unique plane. It cuts out from the sphere an equator, and the segment of this equator which joins these 2 points is exactly the curve of the minimal length joining these 2 points. So here it can be seen exactly, also using this Wick rotation, that to obtain geodesics we just have to cut this hyperboloid by the planes passing through the origin. So by cutting this hyperboloid with the planes which are passing through the origin, we can encounter several situations. First situation is when the curve which is cut out by this plane on the hyperboloid is ellipse. This corresponds to the segments of these ellipses are space-like geodesics. Then if we cut like this, we cut out hyperbolas. Segments of these hyperbolas are time-like geodesics. And if we cut by a plane which cuts this hyperboloid under the angle of 45 degrees, we obtain two straight lines which are generatrix of this hyperboloid. Everyone knows that to obtain a hyperboloid, you have to take just a straight line and rotate it around orbit it around along some circle. Then you obtain a hyperboloid. So these lines I call generatrix. So if you take a plane which cuts this hyperboloid under the angle of 45 degrees, you obtain two light-like lines in ambient space and light-like lines on the hyperboloid. And these are light-like geodesics in two-dimensional de Sitter space. So this classifies all possible types of geodesics in de Sitter space. And the situation is very similar to the sphere, which can be seen from the Vig rotation.